In this question, we are going to look at a classic potentiometer circuit. So let's check it out. This is a circuit that is given. And it says here that contact T is placed on the wire and move along the wire until the galvanometer reading is 0. Okay, and the length xt is noted. So the length from here to here is noted, and the galvanometer reading is 0. In order to calculate the potential difference per unit length, so this is what we want to find, potential difference per unit length of the wire XY. So the wire is actually here, guys. This is the wire. Okay. Which value must also be known. All right, interesting. EMF of E1, E2, the resistance of R, or the resistance of the wire XY. So since we can only choose one of the 4 options, we need to be able to have one, and then that immediately allows us to measure the potential difference per unit length. Okay, guess what? If I want to find potential difference per unit length, I already know the length of xt. Okay, it says here, length xt is noted. So this one I already have, no problem. But what I actually need is the potential difference from x to t. So I need to be able to find Vxt. So if you think about your understanding of potential circuits, right now, if there is no galvanometer reading, or the galvanometer reading is 0, meaning there's no current flowing here, no current flowing through the meter. So I know that the potential difference from x to t must be equal to E2. So we've discussed this in the theory before. Okay, or in other words, if you really want to map out the whole thing, everything around here is E1, 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 and then by this point here, you reach E1. Okay, just like this point here is also E1. Okay, and let's say this point here is Vt, potential difference at T. And let's say this point here is V, I don't know what to call this, guys. Maybe Vg, because it's beside the galvanometer. So for current to not flow through the galvanometer, the potential difference of T, the potential difference at this point, must be the same as this point. Because if not, current will flow either from the higher potential if T is higher, or from the lower potential if G is higher. So right now, there's no current flow. So here and here is the same. But also at the same time, both sides is E1, correct? So in order to find Vxt, I would take E1 minus Vt. And then to find Vg, I would take E1 minus Vg. I mean, to find E2. Okay, so the drop in potential from here to here is minus E2 because you're fighting the battery. Okay, the battery, this E2 doesn't go in the same direction as E1. E1 wants the current to flow. If you look at E1, E1 wants the current to flow like this. But E2 wants the current to flow like this. That's why it is minus, because E1 has to do the extra work to overcome the EMF of E2. All right, so that's why at this point here, you have E1, you minus E2, you will get Vg. Okay, and then at this point here is E1, you minus Vxt, you will get Vt. So in the end, this is what you will get, All right, so sometimes we can fast forward these two if we are already familiar with the circuit. We see something connected in parallel like this. Okay, there's a parallel connection here. So xt must be the same as E2, so that this is 0. Because on both sides, we start E1 the same. That means the potential here to here must also be the same. Here is the same. Here is also the same. Okay, so what will happen? Nah, here is the same. Here is also the same, so that current will not flow. Then I can say here to here must be the same as here to here. Okay, so from here, I can actually use E2 over the length of xt. So the only thing I need is E2, okay? Not the rest. I mean, I could find Vxt using, for example, if I know E1 and R. E1 and if I know E1, R, and the resistance of wire XY, then can. But I can only choose one. So P. All right. Okay, that's it for this question. I'll see you in the next one. Or try more on your own. All this needs experience. Bye-bye.